What is the runtime complexity, bigo, of the following pseudocode? I recently had a very intense debate about the runtime complexity of a super simple algorithm with a colleague of mine. In the end we both agreed to disagree, but as I've been thinking about this, it's challenged my basic understanding of computer science fundamentals, and so I therefore must get additional insight on the matter. Given the following Python, what is the bigo runtime complexity? Now, I immediately called out that this is simply on the order of ON, aka linear. Meaning it's dependent on the length of the string, so therefore this loop will grow linearly as the length of the string grows. My colleague then said, no, it's constant because we know that for the set of all strings we are dealing with, in our case, the max string is always 255 characters long, in our case, therefore it must be constant. He followed on by saying because we have a max upper bound on character length of the string, this results in O255, which reduces to O1. Anyways, we went back and forth, and after 45 minutes of both of us drawing sketches we both deadlocked on the issue. My question is, in what world or what math system is the loop above a constant time loop? If we knew our upper bound was say 1 million characters and the set of all strings could be anywhere from 0 to 1 million, this loop will obviously exhibit linear running times depending on the size of the string. I additionally asked him if he also thinks the following code is O1 if the upper bound size of n is known. Meaning we are certain this code will only ever operate on a max upper bound of say 255 characters. He said this is also constant time, even after I explained this is an ON squared algorithm and demonstrated that the following code would produce a quadratic curve. So, am I missing some theoretical concepts where any of the above is true depending on how the theory goes? Just to be clear, his understanding is that I am correct if n is not known. If the upper bound of n is always known, he is asserting that the two algorithms on this post are both of constant runtime complexity. Just looking to maintain my sanity, but perhaps if I'm wrong there's certainly some additional learning I can benefit from. My good colleague was very convincing. Also, if anybody has additional links or material on the subject specific to this question, please add to the comments.
Applying bigo notation to a single scenario in which all the inputs are known is ludicrous. There is no bigo for a single case. The whole point is to get a worst-case estimate for arbitrarily large, unknown values of n. If you already know the exact answer, why on earth would you waste time trying to estimate it? Mathy, computer sciencey edit. Bigo notation is defined as n grows arbitrarily large, fn is OGN, if gn greater than or equal to cfn, for any constant c, for all n greater than some known. Meaning, your opponent can set c to 11 quadrillion and it doesn't matter because, for all points to the right of some point min, the graph of 11 quadrillion times fn will lag below gn forever. Example, 2n is less than or equal to n2. For a short segment of the x-axis that includes n equals 2, 3, and 4, at n equals 3, 2n is 8, while n2 is 9. This doesn't change the fact that their bigo relationship is the opposite. O2n is much greater than ON2, because bigo says nothing about n values less than n. If you set min to 4, thus ignoring the graph to the left of 4, you'll see that the n2 line never exceeds the 2n line. If your opponent multiplies n2 by some larger constant c to raise his n2 line above your 2n line, you haven't lost yet. You just slide min to the right a bit. Bigo says that no matter how big he makes c, you can always find a point after which his equation loses and yours wins, forever. But, if you constrain n on the right, you've violated the prerequisites for any kind of bigo analysis. In your argument with your coworker, one of you invented n max, and then the other set min somewhere to the right of it. Surprise, the results are nonsensical. For instance, the first algorithm you showed does indeed do about n work for inputs of length n. In the general case, if I were building my own algorithm that called it n times, I would have to consider mine a quadratic of n2 algorithm. Again, in the general case. But if I could prove that I would never call your algorithm with an input greater than say 10, meaning I had more information, and could thus estimate my algorithm more precisely, using bigo to estimate your algorithm's performance would be throwing away what I've learned about its actual behavior in the case I care about. I should instead replace your algorithm with a suitably large constant, changing my algorithm from Cn2 to C10n, which is just bigger n. I could honestly claim my algorithm is linear, because in this case, your algorithm's graph will never rise above that constant value. This would change nothing about the big O performance of your algorithm, because big O is not defined for constrained cases like this. To wrap up, in general, that first algorithm you showed was linear by big O standards. In a constrained case, where the maximum input is known, it is a mistake to speak of it in big O terms at all. In a constrained case, it could legitimately be replaced by some constant value when discussing the big O behavior of some other algorithm, but that says absolutely nothing about the big O behavior of the first algorithm. In conclusion, O Ackermann n works fine when max is small enough. Very, very small enough.
In your case, I am tempted to say that your friend is softly wrong. And that's because of the considerably big additional constant of 256 in O1 runtime. Your friend said that the execution was O256. And because we ignore the constants in big O, we simply call O256 times 1 as O1. It is up to you to decide whether this constant is negligible for you or not. I have two strong reasons to say that you are right. Firstly, for various values of n, your answer of ON and first code gives a better approximation of the running time. For example, for a string of length 4, you say runtime is proportional to 4, while your friend says it is proportional to 1, or 256. For string of length 255, you say the running time is proportional to 255, while your friend again says that it is constant time. Clearly, your answer is more accurate in every case, even though his answer is not outright wrong. Secondly, if you go by your friend's method, then in one sense you can cheat, and say that since no string can go beyond your RAM plus disk size, therefore all processing is in O1. And that's when the fallacy of your friend's reasoning becomes visible. Yes, he is right that running time, assuming 1 TB hard disk and 8 GB RAM, is O1 TB plus 8 GB, 1 equals O1, but you simply cannot ignore the size of your constant in this scenario. The big O complexity does not tell the actual time of execution, but just the simplistic rate of growth of the running time as the value of n increases.
You're both right in a way, but you're more right than your colleague. Edit, nope. On further thought, you're right and your colleague is wrong. See my comment below. The question really isn't whether n is known, but whether n can change. Is s the input to your algorithm? Then it's on or on squared. You know the value of n for this particular input, but a different input would have a different value, so knowing n for this input isn't relevant. Here's the difference in your two approaches. You're treating this code as if it looked like this. But your colleague is treating it like this. In the latter case, that for loop should be considered O1, because it's not going to change with different inputs. In the former case, the algorithm is ON.
I think you're both right. The runtime of the first algorithm is linear in the size of its input. However, if its input is fixed, then its runtime is also fixed. Big O is all about measuring the behavior of an algorithm as its input changes. If the input never changes, then big O is meaningless. Also, ON means that the upper bound of complexity is n. If you want to represent a tight bound, then the more precise notation is theta, n, theta notation.
If you want to see more, please consider subscribing.